In this lecture, I will discuss the buckling of laminated plates, and first I will consider the buckling of simply supported plates under compressive edge loads. So in this case, the four edges of the plate will be simply supported, and we will solve this buckling problem of this kind of bounding condition using the so-called Navier method. And we will also consider the Levy solution in this lecture. So that Levy method will be applicable to plates where the two opposite edges will be simply supported, and the other two edges will be either free, clamped, or simply supported. And I will consider only the specially orthotropic laminates in this lecture, and the governing differential equation for the specially orthotropic laminates with two edge loads nxx and nyy. So biaxial compression, we can say, and they are compressive loads, so arrows going like pointing out towards inside of the plate, and we are not considering the nxy in this case. And we know that due to the application of this load, initially when the load is less, the plate will remain flat, and after certain point of the loading, the plate will start deforming out of plane, and that will be considered as a different equilibrium path, or the bifurcation of the plate out of plane deflection, and that will be termed as the buckling instability of the plate. So that is considered as to be a failure mode because it loses stiffness to carry load. Therefore, the buckling analysis is important to the designer when they deal with these plate structures. So the magnitude of the buckling load depends on both the geometry, then material properties, and the mode shape we are dealing with. Like the first mode will have the lowest buckling mode, and then some, if I introduce some bounding condition to avoid, or some probe or something to avoid this mode, then it may go to the higher mode and buckle in that higher modes. Now let us discuss the governing differential equation, and I will suggest that before listening to this lecture, you please listen to my other lecture where I have discussed the vibration of laminated plates, and there both this Navier method and Levy method has been discussed, and from there you can see like how this differential equation from a general case how we can get this reduced form of this differential equation. Let me go back to that equation which I discussed in that lecture. So I mentioned that for a special orthotropic plate we'll have this equation, where for vibration we get these 5 terms as highlighted in yellow color, but for the buckling case what we'll have Q which is 0 because we don't have any out of plane loading, and this time derivative terms also will be 0 because we are not dealing with something in dynamic behavior. However, we'll have this n, that is the nonlinear term, and this will contain nxy and nxx and nyy. So that together with this first 3 term will be your the governing differential equation, which is shown here. And for this case, we are not considering nxy, so we'll have nxx and nyy. Now, we'll try to see how we can solve for this case of buckling failure or buckling load prediction. So for that, we'll take these two loads as related by this. So let us say nxx is some n0 and then nyy will be k times n0. That means the load in the y direction is always k times to the load of the x direction. So that ratio remains same. So as we increase the nxx, we also should increase the nyy with the same fraction as it is indicated by this k. So that you have to maintain always. So with this, now let us see how we can solve this buckling problem for simply supported plate. And the Navier solution goes very similar way as we have done earlier. So you assume the double sign series and then put that in the governing differential equation. We get this form of the equation. After that, we can show that to hold this equation for every x and y, we should have this term within the bracket 0, and from there we'll get what is this n0, which is a function of m and n, and this is the expression where dmn is expressed in this way. And alpha and beta also consider mn. So you can see in this case, this mn is both in the numerator and denominator. So for each m and n, we'll get one unique value of n0, and the critical buckling load will be the smallest of this n0 mn. So here I want to point out that it's not like very easy to predict which mn will give you the lowest buckling load. Sometimes for different aspect ratios this changes, and if and we can see what I'm talking when I'll demonstrate some calculation using MATLAB. Alright, so now if we have uniaxial case of compression, then k can be considered 0, and then nyy is 0, and we'll have a simplified form of equation. Here you can see the critical load is a function of this, where in the numerator you have m and n, but in the denominator you have only m. So if we examine this equation, then you can see this will be 0 for n is equal to 1, and then n0 will be a function of this. So here and there will be m square, and in this term there is 1 by m square, or 1 divided by m square. And then the critical load will be minimum of this. So you can see that is a function of m. So you have to find out which m will be, and also you should remember that m should be always integer. So we cannot get a fraction value of m, because that is the half sine wave in the Fourier series. So which integer m we have to determine that give you the minimum buckling load. For example, let us consider the stiffness values as this. So d11 by d22 is 10, and the other stiffness values are related in this way. So this is some simplest possible kind of assumption we can take, and then we see that n critical, or n0 m comma 1, so n is always 1, so n0, which is function of m now, will become this. So now we can see for different aspect ratios and different aim, we can get different values. So now let us first set the aspect ratio, let us say for say square plate. Now after checking this expression, we can see uh, that the critical value of the buckling load will be with m is equal to 1, and that is this. Whereas when you take a aspect ratio 2, that is a by b 2, then we'll see that in critical will be something lower. So for longer plate it is becoming lesser. Critical the buckling load will be less, and again it is m is equal to 1. So the mode shape is two half sine waves in both x and y. Means one sine wave in x and one sine wave in y. But when a by b is 3, then we can see the minimum value of this n critical corresponds to m is equal to 2. So m is equal to 1 will give you higher value of the n critical, and that critical value, the non-dimensional value is this. And whereas m a by b 4 also will give solution the minimum value with m is equal to 2, and that's this value. So we can also see that between aspect ratio 2.6 and 4.44, the buckling load is minimum for n is equal to 1 and m is equal to 2. So if I increase the aspect ratio beyond 4.44, then m is equal to 3 will be the minimum buckling load. And if we go lesser than 2.6, the aspect ratio is less than 2.6, then m is equal to 1 and n is equal to 1 will be your lesser load. And between 2.6 and 4.44, it will be m is equal to 2 and n is equal to 1. So that means aspect ratio, depending on aspect ratio, the minimum value will change. All right, so that this is also one important point, that when you go like go on increasing the plate aspect ratio, you can see you'll get higher modes. That means the number of half sine waves will be increased. So you can like if you try to plot this non-dimensional buckling load for different AMs by changing the aspect ratios. So let us say if we set n is equal to 1 for all cases, and then try to minimize the n critical for different AM. So let us say first choose m is equal to 1, then plot the non-dimensional load for every a by b. We'll get this curve. So this is the curve we'll get. And then if you take m is equal to 2 and change the aspect ratios, then you'll get this curve. And then set m is equal to 3, and for all aspect ratio you'll get some curve like this. And then the lowest between this value, so that is the solid line here. These are actually initially they are, let us say, dotted using drawn using dotted line, and then the solid line will be the minimum value. So now if you can see for when if your aspect ratio is between 0 to this value, so this is not done in true scale, so this is just handwritten graph. So the values in the x-axis may not be exactly pointing to that actual number, but you can see that when the aspect ratio is less than this value, which is highlighted by yellow color, so then the minimum buckling load will be corresponding to m is equal to 1. Whereas beyond this yellow color to some point which is after aspect ratio 4, you'll see that M will be 2 is the lowest buckling load. After that, it will be 3 up to certain point, which is, let us say, the 6 point something. And then it will be 4 and 5 like that. So as the aspect ratio will go on increasing, you will have more number of half sine waves in the mode set. So we can also see this in the MATLAB demonstration. And now for isotropic plate, we just show the simplified formula. So for square plate, it turns out to be this simple. So it is 4 times pi square d by b square. And now we have also some tabulated results for this symmetric cross-ply laminate 090 symmetric. And then if you have both uniaxial and biaxial case for different material properties and aspect ratios, this is the non-dimensional buckling load reported. Now let me go back to my MATLAB calculation here. So this MATLAB calculation is for the Navier solution, and here the m is equal to 1 and n is equal to 1 is the first calculation we'll do for these two values, and then this is this k is equal to 0 is for uniaxial. So let's make it 0 first, and then this is square plate, and these are the stiffness values which will give you this condition about the relation between D's, D11, D12, and D22, D66. So this relation, and then you just write down this alpha, beta, DMN, and then n critical is the dimensional value, and then non-dimensional, and then the mode safe. Okay, so we are doing some calculation for m is equal to 1, n is equal to 1, and aspect ratio 1. That means a is equal to 1, b is equal to 1. So let us run that and see. Alright, so I get something 13, and this is the mode safe. So if I go back and see what is the tabulated results, yeah, you can see for a by b1 it is 13 with m is equal to 1. Now if I take a by b2, I will get 8.5. So let us see whether you get that or not. So a is equal to 2 will give you a by b2, 8.5. Then if I change to a by b3, so let us say a by b3 is 3. Now if I run, I get 12.11. Now let us see what is happening here. So a by b3, but here you see it is 8.69, and with m is equal to 2. So I have just set m is equal to 1, then I am getting a 1 higher value of this one. So the lowest value is corresponding to m is equal to 2. So that we can see from here. You can say 8.6944. So this is exactly that. So for a by b is equal to 4, you can also see this. So change this value to 4. A by b4, that's a is equal to 4. 8.5. So this is 1. So you can see for this plate aspect ratio, if I put m is equal to 1, it will give 18.62, which is higher. Even m is equal to 3 also will give you higher, 9.4. So the lowest, which is giving you this to 8.5. Alright, so this plot also I can generate, and let me try to show you that. So this is for this plot, and I have changed the aspect ratios here from 0.5 to 12 with 100 data points, and you can go through this code. This is nothing but for different aspect ratio I am calculating the number or the non-dimensional buckling load by setting m is equal to 1 and n is equal to 1, and then I can change the m is equal to 2 and see what is this curve looks like. So what I'm going to do, I'm trying to replicate this kind of behavior, or this I'm trying to produce these curves. Okay, so first m is equal to 1, and always we are keeping n is equal to 1 for this case. So this is uniaxial case, so n is equal to 1 will give you the lowest buckling result, and now we have to change only m. So we'll change m from 1, 2 and 3 because it takes only integer value, and we'll see how the non-dimensional buckling load varies with respect to the aspect ratio. Okay, so aspect ratio range we have taken from 0.5 to 12, so some number like this. Alright, so let us take this first curve. Okay, so this is the curve. Now I'll use hold on, so you can see when I have. So this hold on command will overwrite this figure with the new figure. Okay, so let us don't change, like we're not changing anything, we're just changing m is equal to 2. And then again run and see what we have got. We have got, so this is the curve for, which is shown using orange color. So this is the next second curve. So it is for m is equal to 2. You can see how it is changing. So let us change here m is equal to 3 and run. Let me see this curve and see now it is the yellow color, and m is equal to 4. Again run. Yeah, so this is some purple color. So all these curves are denoting the non-dimensional buckling load. Now we have to see for which aspect ratio we get the minimum value corresponding to which m. So here for aspect ratio around 2 we get m is equal to 1, aspect ratio around 3 and 4 we get 2, then 5 and 6, between 6 we get 3, and then after 6 we get 4, and then we have to see like how long we can get for 4. If I just put 5 here, you can see the 4 is up to maybe 8. After that we'll have 5. So this way it will change, and you can notice also one nice thing, that the minimum value for all these cases will be same. So the minimum value of the non-dimensional buckling load is actually is same for all this different m. Okay, and that number maybe we have to just find out like which this not definitely like the aspect ratio with integer values. Maybe we'll have to set some aspect ratio which is a fraction. We have to find out that. Maybe we have to do some calculation and see that. Okay, so this is your this plot. Now let me try to see how we can get this the other table. So for this table, the material properties are taken as this. So we want it to vary it, and D12 and E12 is this. Then k is equal to 0 is uniaxial, k is equal to 1 biaxial, and here aspect ratio also is changed to 1 and 1.5. Then E1 and E2 varied. So for all these cases, the values are reported. So to do that, let me go back to this Navier solution, and then here I should comment this thing because this is the relation for this the results which I have shown in the beginning. But now I will uncomment this one so that the D matrix will be calculated for this particular material properties and this laminate sequence 0, 90 symmetric, and the D values will be taken from there. And then k is equal to 0 will be uniaxial, then I'll put m is equal to 1, which is the first, the minimum value hopefully we'll get with that m and n, because we are setting aspect ratio close to 1 and 1.5, so that is the m and n which will give minimum value. But when you change aspect ratio, you have to check. Okay. All right. So now let us take aspect ratio 1, which is a is equal to 1, b is equal to 1, and then let us run this and see. 6.9611 is equal to 1 and k is equal to 0 and this number. So here we have set the e values to 20. We want it to 20. So if we change to 10 and then if I run, I'll get 6.3471, which is this one. And then as differential aspect is 1.5, we'll get this here 1.5, then run, we'll get 5.2768, which is this one. So now if we change to k is equal to 1, we'll get the result for y-axial case. K is equal to 1. Then if we run 1.6236, this one. So 1.5 and k is equal to 1. So this way you can get many other results. You just change those values in the MATLAB. Now I'll quickly go through what is Levy method. We know that these two edges will be simply supported. Y is equal to 0 and y is equal to b, and then the differential equation is taken in this form. Then the solution is assumed as this. This is the same which we have done in bending and vibration case. And this solution gives the simply supported boundary condition at these edges y is equal to 0 and b. And after putting this assumed solution to the differential equation, we get a ordinary differential equation and the solution of this ordinary differential equation. Okay, for this case we are assuming an x is equal to 0, and the general case solution is this, where lambda 1 square lambda 2 square will be denoted by this. And we see that the lambda I, these lambda i's are actually calculated from the roots of this characteristic equation. Now after putting the boundary conditions, we'll get 4 equations, because we'll have to apply 4 boundary conditions. Then 4 equations, and from this 4 equation we'll get an eigenvalue problem as we just been done for the vibration case. By solving this eigenvalue problem, we can get the buckling load, and after that solving the A, B and C's, we can get the mode shapes. So typical result, so here E1, E2 varied, then material properties are taken in this way, then this is the non-dimensional buckling load, and then square plate, symmetric, cross ply 0, 90, 0 for this case, and each layer same thickness. So then for 2 cases I am showing, we simply supported and simply supported, clamped, simply supported, clamped, For this, we can see how we can calculate the buckling load. So if, this is done again similar with similar codes which we have done for the vibration case. So I'll just put this buckling Levy solution SS, simply supported, and here we have used the Newton-Raphson method to solve the characteristic equation, which is again transcendental. So we have many roots. So I have to give a guess value, and first one, it is the simply supported one, and from the table I can see. Okay, so let me see which. So it is the ratio 20. So and then to explain this code, it is nothing. It is similar to the Navier solution equation. Sorry, not Navier solution. It is similar to Navier solution in the vibration case. So here you just define this with beta, then define the lam1 and lam2, and then w. Okay, and then the bounding conditions for simply supported on this too. That will be 0. So you get 4 equation, and then determinant m is the f, which has to be taken out for this Newton-Raphson. So here input is the non-dimensional m critical, and then we dimensionize here, and then put in this formulas. Okay, so for now I'll use this run command. So here we know that solution is near 18, so I just put 18 or 17 or something, some number, and then 19.7123, that is the number we got, and you can see for 20 the 19.712. So if I change to 10, then I should get some number which is close to 11. So let us change to, okay, let me leave this name here now. Okay, so here I will change 10 here, then save, then go to run, and you can start from 17. Let me see whether I get some number. Yeah, so that has given 11.491. 11.492 here, so it's close. And similarly, like we can use the clamped case also similarly. So you can also do it for other boundary conditions, and see how we can change this code and get this numerical values. With this, I'll stop here. So I'll suggest you to go through the reference books and get more details on this. Okay, all right. Bye for your next video.